So today we are using our new tool. Our new tool that we're using today is a spectrometer, right? Spectrum, I think thermometer, thermometer, the origin of the word, therm meaning heat, meter meaning measuring it. So a thermometer is a thing of measuring heat, temperature. Spectrometer is a meter that measures spectra, right? So it's a light measurement. What we have is a box that has a couple of different parts. One is, on one side, we have this square hole, and on one side we have a light, and that light is giving off basically an entire rainbow of colors, if you will, the entire rainbow of colors. Then what happens is the light passes through our square hole into, we put a square peg, right? Our square peg then absorbs some of that radiation, and then some of the light passes through our sample and goes to the other side. Now on the other side is basically, if you will, a prism, right? So remember what a prism does is it breaks our component, our several different colors, and breaks it into individual colors, right? And so we basically have a little prism that is on a very quick motor, right? And then somewhere down here we have a little detector, and all that detector does is mark every time a photon hits it. It gets excited, and it just registers as an electrical signal, I've been hit by a photon, and it just counts it, right? So what happens is I put in my sample, and what will happen is the spectrometer will, the light is going through, and the prism is adjusted at such a point that for a brief moment in time, the light that is 400 nanometers is hitting my detector, right? And it sits there and it counts it for a few milliseconds. And then the prism turns just a little bit, right? Prism turns a little bit such that now the color photon that's hitting the detector is 405 nanometers. It waits there for a couple of milliseconds, counts that. Then it turns again. Different frequency, count. Turns again, different frequency, count. And it does that several times a second, going back and forth over all of the different wavelengths, right? And so what it's measuring is what is known as absorbance. Absorbance. Now, absorbance is a mathematical construct. We have to talk about it for just a brief second. What spectrometers used to do, if you will, is calculate percent transmittance. So I have some intensity I of light going into our, what's called our cuvette, right? So a certain amount of intensity of light goes in, goes through my colored substance, and then a certain amount of light intensity comes out, right? So literally, how many photons of light per unit time go in, how many photons of light go out, right? And so we used to define something called percent transmittance. Percent transmittance is I divided by IO multiplied by 100%. We would expect, as I increase the concentration of our substance, right, if I increase the concentration, what will happen to the percent transmittance? It will go down. Does that make sense? Right? Because more as I make this darker and darker, the intensity is going to go down because more is going to be absorbed. And that is in fact true. Percent transmittance does go down, but the problem for us is that it goes down in a logarithmic fashion, right? Which sucks. And the reason why it sucks is because doing equations and figuring out the equation of this logarithmic thing is just kind of a pain, right? Now spectrometers have been figured out as a concept, decades and decades and decades ago, long before we had computers to do our math for us, right? So if we were to do this experiment, say back in, I don't know, the 1950s, our lives would be very difficult because we'd have to figure out this logarithmic equation by hand, right? So what we did is we invented a new concept. We invented a new concept, and that is absorbance. And I will just tell you that absorbance is sort of proportional to the log of the percent transmittance, right? And we just made this up. We made this up, and it's just a mathematical construct of percent transmittance. But here's why we did it. We did it because of this relationship. We know that it's logarithmic versus percent transmittance, that if we do a graph of concentration versus absorbance, then we actually get a straight line, which isn't very straight. We get a straight line. And the reason why we would rather measure absorbance instead of percent transmittance is because dealing with the equation of a straight line, that's something I can teach a ninth grade algebra student to do. Right? So it just makes our math way, way easier, which is why we only measure absorbance. And in fact, this spectrometer was made in the last 10 years, and I can't even convince this thing to give me a percent transmittance. It will only give me absorbance. Nobody does percent transmittance as the like. So as you can see sort of here on the bottom, the way our spectrometer works, we have two columns, and there is a particular wavelength, and then there is a particular absorbance at that particular wavelength. One of the things about this Beer's law plot, this straight line, is that the absorbance and this relationship, absorbance being equal to the molar absorptivity times the path length times C, that's our Beer's law, that's what we're using today. This only works if all of our absorbance measurements are taken at the same wavelength, right? Because as you can see, what the absorbance is depends on what the wavelength is. So when we do our graph, where we're going to make a series of solutions of different concentrations and measure their absorbance, all of our wavelengths have to be done at the same wavelength, right? So if I look at this particular, so this is the soda sample. If I look at this particular absorbance spectrum, I can sort of see that the absorbance depends on what the wavelength is, correct? So as we dilute our solutions, what is going to happen to this curve? If I dilute this sample, and it'll become lighter, what will happen to the absorbance? It'll go down, right? Because less is being absorbed because there's less colored stuff in there. Okay, so red number 40 absorbs at many different wavelengths. As you can see, it absorbs at all these different wavelengths. So the question is at what wavelength should we be measuring our absorbance at? Where on this graph should we choose to, okay, this is where I'm going to measure the wavelengths all day long? Well, don't we want discernment? Don't we want our number to be telling, right? So we don't want to measure like up here, right? Because if I dilute my stock solution by half, this absorbance is going to go down barely at all, correct? So we want to measure our absorbance up here, right? So for today, so that's why I kind of did it here in this wavelength, is because I wanted to see, it looks like our wavelength is about 512 nanometers, right? That is where the absorbance is the highest. So 512 nanometers is what we are going to measure all of our measurements at, right? It's really important that we always take it at 512. Now we have another problem that we have to deal with, and that is we have to recognize that, okay, when I put my cuvette in there, quick side note, some of these cuvettes have sort of like a set of sides that you can see through, and the other side has a bunch of lines. It's almost kind of like frosted, right? You need to make sure when you put the cuvette in that the light goes through the side that you can actually see through, right? The reason why we have sort of like the frosted side is such that, oh, okay, well, I always touch this side. That's where you put your grindy fingers, and you never touch the sides that have the plastic that we want to go through. But when I put my cuvette in there, the light is coming through. Isn't the light also being deflected or reduced by the piece of plastic? Isn't it also being deflected a little bit by or absorbed by the water that's in there? It is, right? So we want, for the Beer's law, right, we want what is the absorbance coming from just the red 40 that's in our solution. We wanted to ignore any absorbance that's coming from the water or any absorbance that's coming from the cuvette, right? We do this with our scales too. We do this with our scales in that when I put a piece of weighing paper on the balance and then I dribble stuff out, I put the piece of weighing paper on there and I hit 0, and I basically say, hey, Mr. Balance, ignore the mass of this piece of paper. We do that with our balance. we're going to kind of do the same thing here with our spectrometer, in that what we're going to do is we are going to calibrate it. Right? Now this is something that only has to be done once every hour or so you don't have to worry about it. I will calibrate it for you. But what we're going to do is we're going to put in what's called a blank, which is just another cuvette and with distilled water. And then what we're going to do is we are going to tell the experiment, we're going to calibrate the spectrometer. It will take mere moments. So now, you'll notice, because I have the cuvette in there, now all of my absorbencies are sort of like dead flat, right? So even though there's something in there and it's absorbing it, it's sort of like saying, it's just like, oh, we're going to kind of ignore it. Because now watch happens when I take the cuvette out, you will see that now the system seems to be registering as if there's an absorbance in there, right? It's the same as if I put a piece of paper on the balance, hit 0, and then I pull the piece of paper off, right? The number that it's going to give me is going to be completely nonsensical, and that's okay, as long as I recognize the next thing I'm going to do is I'm going to put some stuff on that piece of paper, put it back on that balance, right? So now our spectrometer is calibrated. So now when I come over and I put in my soda sample, now it's a much cleaner curve, as you can see. And now what we can do is we can say, oh, okay, cool. So my soda sample, my absorbance of my soda sample at 512 is 0.187. So that is the absorbance that we are going to start today with our soda sample, right? We've now measured what the absorbance of the pure soda sample is, calibrating today. Do we care about the wavelengths down here and the wavelengths down there? No, we don't, so we want to not confuse ourselves. So what we're going to do is we are going to, I'm going to make our pretty picture. We're going to change our presentation and now have our spectrometer. Oh, it wasn't 509. 512. There we go. So now our spectrometer is calibrated, and now it is all set up for us to do our work today, right? So you're going to be making a series of solutions, and you have to measure the absorbance of each one of those solutions. So you're going to have a cuvette, which you're going to clean out. And when you're ready, you're going to come up, and you'll notice that this kind of flops around a little bit, right? Flops around because of ambient light and such. So the way to do this is you're going to come up, you're going to drop in the cuvette, you're going to kind of turn your head, count to 3, go back, take that number, and walk away, right? This is not like a balance where you have to let it set and stabilize. The number that is registering there is basically the average of the last 3 seconds worth of runs. The last 3 seconds worth of runs, right? And it will always be slowly updating. It might flop around a little bit, although it's looking mighty stable right now, right? The reason why you have to drop it in and wait a couple of seconds is because you need to make sure that you're getting the last 3 seconds, of which that number is an average, right? Sort of like a moving average, okay? So that is our absorbance. Now, the only reason I brought this one over here is one of the things about these cuvettes is that you're going to be tempted to make them clean and dry before you put your solution in them. And because they're so small, you are going to be tempted to rinse them with acetone before you blow them out. You can't. This is what happens when you put acetone into one of these cuvettes, which is the only reason why I keep this one. It frosts the plastic, right? So you cannot clean these with acetone. But we're going to talk a little bit later about why you don't need to. Cool? There's your crash course on how to use a spectrometer.